Hi everyone, welcome to my lesson about the stack data structure. It ends with a little task for you to do. In this lesson, I'll explain what a stack is, the different operations you can do on a stack, the benefits and limitations, in other words, evaluating the stack, and the main ways that a stack is used in modern computing. The stack is a data structure like a list or array. But unlike them, the program can only access a single item of data. So a stack can have many data items in it, but the computer can only get at one data item, and that's an item at one end of the stack. And the end that you can access, that you can get to, is called the top of the stack. Adding an item at the top of the stack is called push, and taking an item from the top of the stack is called pop. So when you push an item, the stack gets longer by one. In other words, the top moves along by one. And when you pop, you get an item off the stack, so you end up with a value, it returns a value, and the stack gets one littler. That is, the top of the stack goes down by one. And those are the only two operations you can do with a stack. So remember those. I think the names are quite self-explanatory. Pushing something onto the stack and popping something off the stack. Actually, as well as push and pop, there are some optional additional commands that some people add to their stack programs. Top lets you look at the top of the stack and see the value that's there without the stack getting any littler. And the two functions isFull and isEmpty will return true false values according to whether the stack is full up, you've used up all the available space, or if the stack's empty, it's got no data in it at all. We'll look at all of these later, and in the next lesson we'll actually write a program to do all these things. So I've drawn a little bit of a stack here. When I do a list, I often do them horizontally, but with a stack we typically draw it vertically. It doesn't really matter because it's just a visualization. Inside the computer it's all done with electronics. Anyway, let's imagine we've got 4 data locations, and the top of the stack is the first data location. Why? Because we don't have any data in the stack yet. So the location that we're going to first add data to is that one, the first location in the stack. That's the top of the stack. We haven't added anything yet. So let's imagine that we want to carry out this command, push A. We're going to push the letter A onto the stack. So A goes into the location where the top of the stack is, and the top of the stack moves up by 1. So it moves to the next data location. So the stack now has 1 item in it, and the top of the stack is pointing to the empty space where we can add new data. So let's do that now. Push B. So imagine the next line of our program is push B to the stack. So we can see where the pointer is pointing to the empty space at the top of the stack. So push B. B goes into that empty space, and the top of the stack moves up by 1. Let's see how pop works now. So our next command is to pop from the stack. Remember, pop returns a value. The top moves down by 1, and the value B is returned from this function, from the pop function. I've wiped B off my picture. Strictly speaking, the computer usually doesn't even bother to wipe its memory locations. It just forgets that it's got a value there and treats it as empty memory. To make that easier, because that's a lot to explain, I've just wiped out the space. So top is now pointing at effectively an empty space at the top of the stack. Let's push another value. So push X. Where does X go? Where the top pointer is pointing. So that's my stack now after all those commands. A at the bottom, then X, and the top of the stack moves up to the new empty space at the top of the stack. So let's put all those together so that you can see how the stack is changing as we run a program. Push A, push B, pop, that returns B, and push X. So the stack, using the stack, we can add and take away values as often as we like. We often call the stack a LIFO data structure. LIFO stands for last in, first out. That means the last data that you've just pushed in will also be the first data that you pop out of the stack. And that's because all the popping and pushing all happens at the same place. So the last thing you've pushed is also the next thing that you would pop. It all happens at the top of the stack. Stack is used fairly often in computing. It's used anytime that you want to access the most recent piece of data. Instead of going for the data in a particular location, if you ever just want the last bit of data. So for instance, if you want to look at something in reverse order, then a stack would be the ideal storage solution. For example, if you do Control Z when you're, let's say, doing word processing or something, if you press Control Z, it will undo the most recent command that you have carried out. And if you press Control Z again, it will go back through your commands in reverse order. And that's how a stack works. Also, if you're browsing the web and you press the back button, it will go back to your most recent visited location and then revisit your locations in reverse order. And the other absolutely classic use of the stack is to stack up all the versions of a recursive function. You remember that when we do recursion, all the versions of the function open in memory one after the other, and then when you hit the base case, they're all closed down in reverse order. The reason for that is that the computer stores all those different versions as a stack, and when you hit the base case, that's the end of the stack, and then they close down in reverse order. There's a load of things you can't do with the stack. You can't insert a value into the middle of the stack because you can only work at the top of the stack. You can't edit anything in the stack. All you can do is take items off it or add. You obviously can't sort the stack because you can't rearrange it. You can't traverse it. You can't use a for loop to go through it. You can't print it out. You can't search through the stack to see if it's got the things you want in it. So stack is mostly about things you can't do. What can you do? You can push, you can pop. That's about it. Now, I've been talking a lot about the things you can't do. Why can't I do them? Why can't I do them? The computer hasn't stopped working. The memory is still electronic. It's still all there. No, instead, we've decided to write software that works with memory in that way. The programmer has decided, okay, I'm going to treat the computer memory as a stack in this program, and I'm only going to write push and pop commands. So if you think about it, the computer still works. It's still got all its powers. It's just that I, or whoever the programmer is, have decided I will only write push and pop commands in this program. Why? Well, there's a really good reason. All the data and input and output, all happens in one place at the top of the stack. So the programs are very, very simple, and the big O value of any stack operation is 1. So it's better than all the other algorithms that we've looked at so far on this course. So it's very, very efficient in time, because the operations are instantaneous, and there's no wasted space because you just pile all the items that you want to store up in a continuous stack. So it's very efficient in time and it's very efficient in space. Of course, there's a price to pay for that, all the things that you can't do. So look at all the operations that you can do with a list, for example: append, insert, edit, delete, traverse, sort, and lots of other things that you can do with a list. With a stack, you can push, which is a bit like appending to the end of the stack. You can't insert, you can't edit, you can pop, and you can't traverse the stack. You can only look at the very top of it. You can't sort it. You can often check if the stack is full or empty, and I hope you've understood that this is all voluntary. It's just that a programmer has decided, I'm not going to do any of those things. I am going to treat this block of memory as a stack, because that's bringing me lots of benefits in terms of efficiency and speed, and I don't need, let's say we're doing a recursive function or something, I don't need all those other commands, so I'm just going to do without them. I'm just going to write push and pop commands, and I'm going to treat this block of memory as a stack. So I hope that has given you some idea about what a stack is. It's just a way of handling a block of memory. There are two main stack operations: push and pop. Sometimes we add is full, is empty, and top, but basically push and pop. The evaluation for stack is that it is very, very efficient and easy way to deal with memory, but in order to get those benefits, you have to give up a lot of commands that we would normally take for granted when we're working with a list, for example. But there are some specific uses, specifically where we want to do something in reverse order or go back through a list in reverse order, and recursion is a classic example. So if you don't remember any of this, I'm going to give you a test in a sec. If you don't remember any of this, you can replay this video and go back over it. It's only about 10 minutes long, so go back and look at any part of it. Okay, so going to be a test, so have a go at these questions. So first answer these 4 questions, and then there's an activity on the next slide as well, so do that as well. Explain why the stack is efficient in both time and space. Explain what the disadvantages of the stack are, and give a real life example where you might use the stack, and say why you might choose to use the stack in that case. And list all the stack operations. It's not going to be a very long list, is it? List all the stack operations and just write a short sentence saying what each of those operations means. So bring that to the next lesson, the answers to those 4 questions. That shouldn't take you long, and I've got a little activity on the next slide, and then we're done. So here's the activity. Draw an empty stack. You know, you can copy the way I did it, a vertical set of empty locations, and show how it looks. So I want you to draw it 5 times, and each time show what it looks like after that operation. So there are 5 operations, so draw the stack 5 times, showing how it changes after each one of those operations. And once again, perhaps write that on the same bit of paper as your test answers, and bring that to the lesson, and that's how we'll start the next lesson, by looking at that. Okay, so I hope that hasn't been too onerous, and we can carry on. We're going to write some programs in Python to create and work with the stack in the next lesson. So hope that you got on okay with that, and I'll see you in a couple of days. Bye for now.